This is Mr. Best. Welcome to section 2.6, Rational Functions and Asymptotes. We're going to focus on the algebra side of things in terms of finding vertical and horizontal asymptotes. We're also going to look at the domain of rational functions. We are going to start with the parent function of a rational function, which is f of x equals 1 over x. But what is a rational function? A rational function is the quotient of two polynomials, just so that the denominator polynomial is not equal to 0, because we know we can't divide by 0. So let's kind of go through the parent function. We want to graph f of x equals 1 over x. Well, normally when we start with the parent function, we start by kind of doing a table to identify what those values are. So if we do a table for x and y, and if we only try to pick nice values, there's only a couple. You can have negative 1, 1 divided by negative 1 is negative 1, and 1 divided by 1 is 1. So you don't have a whole lot of values here when you're just looking for nice ones. So we'll go beyond that. We'll do negative 2. That would give us negative 1/2, and positive 2, which would give us positive 1/2. So at negative 2, we're at 1/2, and at positive 2, we're at 1/2. And you can see if we go negative 3 and 3, we will get negative 1/3 and positive 1/3. So you can see that they're getting closer and closer to that x-axis. If we go in the other direction and do negative 1/2 and positive 1/2, 1 divided by 1/2 is 2. So we would get negative 2 and 2. And if we try to graph those, you can see that the graph, or those points, are getting closer to the y-axis. So we have a rational function in terms of its parent function looking like this, where the graph gets close to both the x and the y-axis, but will not touch either one of those axes. So what's the domain? Well, the domain, we start with all real numbers, and then we identify that the denominator cannot equal 0, so the domain would be all real numbers, excluding 0. The range, the same thing. The range goes up and down forever, but it never crosses the x-axis, so your range is negative infinity to infinity, excluding x equals 0. There are no intercepts. It doesn't cross the x or the y-intercept. It is decreasing, and if you take a look at this, and remember reading this from left to right, as you read this from left to right, the graph is going down. You can see quadrant 3, it's decreasing, and then when you pick it back up in quadrant 1, it continues to decrease. So it's decreasing on the interval from negative infinity to 0. And then at 0, it's not even part of the graph, so then it continues to decrease from 0 to infinity. It is origin symmetry, which means that it rotates around the origin 180 degrees, which also indicates that it is an odd function. So we remember from an odd function that f of negative x is equal to negative f of x. We have a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. So these would be these dotted lines indicating that the graph, as it goes to infinity, gets closer and closer to each of these horizontal and vertical lines. So there's the parent function of the rational function 1 over x. And we'll do more on the graphing side when we get to section 2.7, but I wanted to at least show you what the parent function looked like and what some of the features are as well. So what is an asymptote? Probably your old definition of an asymptote was a line that the graph approaches but does not touch. And to start off, that's a decent definition when you're first learning about asymptotes. But as we move forward here, that's not really an accurate definition of what an asymptote is. We have two types that we'll be talking about today. There's 3 total that we will talk about. The third one will be a slant or an oblique asymptote, and we'll talk about that later. The 2 that I want to talk about today is the vertical and the horizontal. The line x equals a will be a vertical asymptote of f if f of x approaches infinity or f of x approaches negative infinity. So as your y is approaching infinity and negative infinity, your x value will approach this a value from the left or the right side. Okay, so that's the more accurate definition. Now, I will tell you with a vertical asymptote, the graph will not touch a vertical asymptote, but that's not true for a horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of f if f of x approaches this b value as x goes to infinity and negative infinity. Once again, we don't care what happens before infinity and negative infinity. We care what happens as it gets closer and closer to that. So you will actually find out that on your horizontal asymptote, sometimes your graph actually crosses the horizontal asymptote. So potentially it could look like this, where it crosses the horizontal asymptote, still approaches it, but it approaches it from the other side. So don't be surprised. So that old definition that we have where the graph approaches but does not touch is not really accurate, especially with horizontal asymptotes. So how do we find these vertical and horizontal asymptotes of a rational function? Well, let's let f be a rational function where n of x represents the numerator polynomial and d of x represents the denominator polynomial. But when we go to find the vertical and horizontal asymptotes, we don't want any common factors between the numerator and denominator. So we need to make sure that we cancel any common factors out. Once we have done that, the vertical asymptotes occur at the zeros of the denominator. So we will set the denominator equal to 0, and we will find the vertical asymptotes from there. The horizontal asymptotes occur at most once for rational functions, and are determined by comparing the degrees of the numerator and the denominator. So there's basically three choices. The degree of the numerator can be less than the degree of the denominator. If that's the case, then we get a horizontal asymptote at y equals 0. The degree of the numerator can be greater than the degree of the denominator, and we will not have any horizontal asymptotes. Or the degree of the numerator could be equal to the degree of the denominator, and if that's the case, we will get the leading coefficients of the numerator and denominator. So where a and b are the leading coefficients of the numerator and denominator. So that's how we'll find that fraction, or that doesn't have to be a fraction, or that value for the horizontal asymptote. So those are the three possibilities for each of the horizontal asymptotes. So now let's take a look at a couple examples, find the domain, and identify any horizontal and vertical asymptotes. So the domain, well, the denominator cannot equal 0. So x plus 3 cannot equal 0. If we solve that, we find out that x cannot be negative 3. So your domain are all values excluding negative 3. So we'll write that in interval notation. Vertical asymptotes come from the denominator as well. So at x plus 3, to find the vertical asymptote, you actually do the same thing. You solve for x and find out at negative 3, which is where it's undefined, you have a vertical asymptote at x equals negative 3. And make sure you write it as an equation. It is a vertical line. The horizontal asymptote, you're looking at the degree. So you have 1, you don't have a variable up there, but if you did, it would be x to the 0 over x to the first plus 3. So the degree of the top is 0, the degree of the bottom is 1. So what we have is a numerator degree is less than the denominator degree. So if it's less than the denominator degree, then we have a horizontal asymptote at y equals 0. And that's how you find each of those. Let's go ahead and look at example B. We got g of x is equal to x squared minus 16 over x squared plus 7x plus 12. So we want to see if, first off, we can cancel anything. So we need to factor these to see if there's any factors in common. So it looks like we'll have a difference of squares and a trinomial of x plus 4 and x plus 3. So our factors on bottom, there's two values that x cannot equal. X cannot equal negative 4 and x cannot equal negative 3. So when you go to find the domain, we want to include all real numbers except for those two. So from negative infinity to negative 4, and then the union, negative 4 to negative 3, and then the union again, and negative 3 to infinity. So that's all real numbers excluding negative 4 and negative 3. The vertical asymptote does not include both of these though, because at x plus 4, that factor cancels out. So even though the factor cancels out, x cannot equal -4 because if you plug it into the original, it's still undefined. But it is not part of your vertical asymptote. So your only vertical asymptote on this one is that x equals -3. There's something else that happens at that x plus 4 that we'll talk about a little bit later. The horizontal asymptote, the degree on top, and you can look at this either in the simplified or the original version, but the degree on top, I'll do it with the simplified. So what we have left after we simplify is x minus 4 over x plus 3. They both have a degree of 1, so you want to take the leading coefficient. So that would be 1 and 1 in this case. So your horizontal asymptote is at y equals 1. So your domain is your restriction of your denominator. Your vertical asymptote comes from the simplified version of your rational function where the denominator is equal to 0, and then your horizontal asymptote, you got to compare the degrees of the numerator and the denominator. So on these last 3 examples, I just want you to identify the horizontal and vertical asymptotes. I would pause the video right now, see what you can do with these 3 examples, and see how you do on each of them. So I would pause the video right now. These are the last examples. Go ahead and find the horizontal and vertical asymptotes, and then check and see if you got them correct. Alright, so you can see I've gone through and went through and found the horizontal and vertical asymptotes. I made sure that there was no common factors. Then I took the denominator, set it equal to 0, solved for x, and that allowed me to find my vertical asymptote. For my horizontal, I compared the degrees, so I had a degree of 1 and a degree of 1. Since they were the same, I took the leading coefficients 3 over 2, and that was my horizontal asymptote for example A. On example B, I went ahead and factored the top just to make sure that there was no common factors. Then I set my denominator equal to 0, and I found out that x could not equal 1, so therefore my vertical asymptote was at x equals 1. So when you write your vertical asymptote, it's that vertical line, x equals wherever it's undefined. The horizontal asymptote, the degree on top was larger than the degree on bottom, so therefore, and that's a 1, therefore there was no horizontal asymptote on this one. And then on the third example, we have x squared plus 1. When I solved that, I came up that x could not equal plus or minus I. Well, we're looking at these on the real plane, so therefore there was no vertical asymptote on this example. There was a horizontal because your degree on top was smaller than your degree on bottom, therefore your horizontal is at y equals 0. So that's how you find the vertical and horizontal asymptotes. Also, you can look and find the domain of each of these algebraically as well. So once again, this section is a lot about the algebraic side, being able to find these things algebraically, and then we will get into the graphing side of things on the next section.